Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today, after much delay, we're finally going to talk about principal component analysis. It has taken me a while to get to making this video. In fact, actually, it's taken me quite a long time to develop everything that I wanted to be in place. The C++ code that we're going to go on to look at is actually quite simple. That didn't take very long, but it was everything else that I wanted to do for the video that's really taken quite a lot of time. Plus, I've been experimenting a bit with some different types of video. Anyway, I don't want to do a long introduction, so we're going to jump right to it, but I just want to say quickly, as I always do, that if you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel. I do try to make videos as regularly as I can. Sometimes I say once a week. I try to do that. I don't always achieve it, but if you subscribe, you don't need to worry about missing anything. Thank you very much. Okay, so without much further ado, let's talk about principal component analysis. Okay, so I really thought I'd start this video today talking about principal component analysis, simply really in terms of showing some examples of what PCA is and what it does, and then we're going to go on to move on to look at the theory of PCA a little bit and look at how we can implement it in C++. Okay, so PCA is essentially a technique for finding the principal components or principal axes of a multi-dimensional data set. Now we're going to have a look at some more concrete examples of what that means in a moment, and also look at the theory a little bit later on. But suffice to say for the moment that what that means is that each of the principal axes represents the directions in which the data has the greatest variance. To demonstrate PCA in action, we would need some kind of multi-dimensional data set. Now there's plenty of data or different types of data and data sets out there that I could have chosen to go on to show some examples of PCA, but my sort of personal area of expertise is image processing, and so I've decided to very much stick to the two-dimensional image arena in order to generate some examples. Now, actually, each frame in this video that you're watching right now actually constitutes a multi-dimensional data set. How can this be? Well, each frame consists of an image, and that image consists of three channels of information, one representing each of the red, green, and blue primary colors that go on to constitute all of the colors that you can see in the image going on here. We can see that very clearly if we separate this image into the three channels from which the overall colors are formed. So all we have done here is to separate this image into the three channels, red, green and blue, which we're now showing as separate layers. If we were to combine these three layers together, we would get back to the original image that we started with. Each image is divided into pixels, something like the ones that you can see here, although in reality, of course, they are actually a lot smaller. These are really just for illustration. And there is a corresponding pixel in each of the three planes, or each of the three channels, corresponding to red, green and blue. Now each of those three pixels will have a number associated with it that corresponds to the intensity of that color for that pixel. So one number for the intensity of red, one for the intensity of green, and one for the intensity of blue. Now if we take each of those, we can rearrange them so that we can represent each pixel by a three-element or three-dimensional vector. We can then combine all of those vectors together for all of the pixels in the image, and if we do that, we can see that we would end up with a matrix representation of our original image. Now that we have our image data in that form, we can actually perform PCA on it if we regard each image as being a three-dimensional data set. Actually, now that we have a three-dimensional vector for every pixel, we can plot those as points in three-dimensional space. So here you can see every pixel from each frame of the video has been plotted as a single point in a three-dimensional coordinate system. Here each axis corresponds to one of the three primary colors or channels in the original image, one for red, one for green and one for blue as labeled. And you can see that as I move around the image here, the shape of the point cloud we have in that three-dimensional space varies accordingly. In fact, if I hold up some colors to the camera, we can see much more clearly what's going on. If what the camera sees is mostly red, we see that all of the points cluster along the red axis. If it's green, we see that they all cluster along the green axis. And for blue, we see that they all tend to cluster along the blue axis, which is pretty much exactly what we would expect. Now, of course, in a natural image such as this one, we can see there's much greater range of colors. There's green going on here, black from my shirt, white or cream here, and the sky comes out just white, and pink from my face. So we get a much broader spread of colors, as we would expect. Now, actually, we can perform PCA on this data set, but the first thing that we have to do is to make it zero mean. So let's do that now. I will go on to explain the theory behind principal component analysis and how we actually calculate the principal components, but let's not worry about that just for the moment, and let's just focus on looking at this example. So if we do calculate the principal components for this data, then this is the result that we get. So you can see that we get three vectors, one corresponding to each of the three principal components that we get for this data, and you can see that the vectors are pointing in the direction of the greatest variance. So the first vector points in the direction of the greatest variance, the second vector corresponding to the second principal component points in the direction of second greatest variance, and so on. Now we only had three dimensions to start with, so naturally we only get three principal components. Okay, so to begin with, we saw how we could divide our image into the three channels corresponding to the red, green and blue components from which it is formed. If we do that, we get something that looks like this. So here on the top left is the original true color image, and then clockwise from that we have the red, green and blue channels respectively. In fact, if I hold up my colored image again, we can see how that works. You can see that in the red image, the red is greatly exaggerated. In the green image, the green is the brightest, and in the blue image, the blue is the brightest, exactly as we would expect. So what can we actually do with the principal components? We've seen these vectors, the arrows on the plot, but so what? Well, what's so interesting about that? Well, we can actually form an image out of each of the principal components. If we do that, we get a result that looks like this. Now, instead of representing the red, green and blue channels respectively, each of these images clockwise from the top right represents the first, second and third principal components of this image data respectively. You can see that they look quite different to the red, green and blue channels when we looked at those individually. The first thing to notice is that the first principal component on the top right very clearly contains most of the information from the image. The second principal component in the lower right contains slightly less information than the first principal component, but still more than the third, that very clearly contains the least amount of information. This is really exactly what we would expect, because as we've discussed before, the first principal component corresponds to the axes about which the data has the greatest variance. Okay, now PCA, or principal component analysis, has a great many applications, and I'm really not going to try and talk about them all, and indeed they're not necessarily that easy to illustrate in video form. But sticking with the theme of image processing, which is my area of expertise, the one that I wanted to talk about was hyperspectral imaging. So in hyperspectral imaging, we have many more channels available than just red, green and blue. We might have multiple channels at the UV end of the spectrum, and we might have multiple channels in the infrared end of the spectrum, and indeed we could go beyond that. This obviously results in a lot of data, and it can be very difficult to handle such a highly dimensional data set. Indeed, it's actually quite difficult to identify features of interest if you try to look at all of the dimensions together at once. In fact, there isn't really any practical way of doing that. So in this case, PCA, or principal component analysis, can be used as a technique of dimensionality reduction. In other words, we can use it as a technique to reduce the number of dimensions of our data. So we've already seen that the first principal component contains most of the information, the second contains the second greatest amount of information, and so on. So we know that the components are going to come out in that order. So regardless of how many dimensions we start with, suppose we had, for example, a 7-dimensional or 9-dimensional data set, we can pick out, say, just the first three principal components, and that would then give us, we know we can actually calculate how much of the information is going to be preserved, and a 3-dimensional data set is much easier to visualize than a 7 or 9-dimensional one. Indeed, if we pull out the first three principal components of a 9-dimensional data set, we could then associate each one of those components with one of the red, green and blue channels, and then we could produce a single true color image, well, in fact a false color image, that would be highly representative of our original highly multidimensional data set, but would show many more of the features. So one application of something like this would be of observing the Earth from space, or from satellites, or from aeroplanes, and making measurements of crop yields or forestation or something like that. Okay, now I can't obviously demonstrate proper hyperspectral imaging with the camera that I have here, because I'm limited to just the three channels for red, green and blue as we've been talking about. But I tried to create an example that will give some indication of really what PCA can do in terms of feature extraction. Okay, so one example is this image here. Okay, now if we zoom into that, now hopefully I can hold it so we don't get too much glare or other reflections. Now if we look at that image just in its original colours, in the original colour image, we can see it's just a uniform green/grey kind of colour, really not very interesting. However, if we look at the principal components, we can see that embedded in that image is a hidden message, and hopefully you can see that that says "Hello World." Okay, so what's happened there is principal component analysis has extracted the dimensions with the greatest degree of variance, and that allows us to exaggerate or to highlight the variance caused by the very slight variations in colour that contain that hidden message. So obviously a technique like this applied to images which have many more dimensions than just 3 can easily extract differences or variations that you might not be able to see otherwise. So there we go, I think just quite an interesting example there. Okay, so we've seen some examples of PCA in action. We've seen sort of roughly what it can do, and we've had a look at why we might want to do that and why it's interesting. Let's go back inside and let's have a look at the theory. How does PCA actually work? And above all, how do we actually calculate the principal components for image data such as this, or indeed any multi-dimensional data that we might want to look at? So, we have seen some examples of principal component analysis, or PCA, in action. But how does it actually work, and how can we implement it in C++? Let's take a look at that now. We have just seen how we can rearrange color image data into a multi-dimensional data set. To do that, we regarded each image as consisting of m by n by 3 data points, as shown here. And we then saw how we could rearrange these into a matrix of m by n rows and 3 columns, as shown here. In the general case, we will be dealing with data that looks something like this. So X will be a matrix with k rows and p columns, where k is the number of observations and p is the number of variables. So we have k observations of p variables. The principal components of this data are actually just the eigenvectors of the covariance matrix of X. Let's take a look at what that means. The covariance matrix can be computed as shown here, as simply X transpose multiplied by X, all multiplied by 1 over k minus 1, where k is the number of observations. Note that this is often written as X times X transpose, the other way round to what I have here, but it depends on how the data are arranged. I have data arranged with a column for each variable, so it should be this way around. But if the data are arranged with a row for each variable and a column for each observation, then it should be X times X transpose. It's important to bear this in mind for whatever data you are dealing with. Just bear in mind which way round your data is and adjust accordingly. So, in this case, the elements of the covariance matrix K will then be as shown here in the lower portion. So the first element is the covariance of the first column of X with itself, the second element is the covariance of the first column with the second column, and so on throughout the rest of the matrix. Notice that for k observations of p variables, the covariance matrix ends up being a square matrix of p by p, regardless of the number of observations. Also notice that the covariance matrix is necessarily symmetrical, as you can see here, where I have coloured the elements accordingly. Each individual covariance could be computed, as shown here at the top, although of course we don't actually have to do this because it is taken care of by the matrix multiplication. But I wanted to show this because it illustrates quite nicely why we have to subtract the mean from the data. Here, xi bar indicates the mean of the ith column of X, otherwise known as the column-wise mean. We can see from the equation for the covariance that it is necessary to subtract the column-wise mean from the data prior to computing the variance. So this is the pseudocode that we would end up with. It is actually quite simple, mostly because we have covered much of the groundwork already in previous videos as we have built up our linear algebra library. So we can see that we first subtract the column-wise mean from the data, bearing in mind that this might be different if the data were arranged differently. We then compute the covariance matrix, and then we compute the eigenvalues and eigenvectors of the covariance matrix. Now, we've already covered how to do that in previous videos, so I'm not going to go over that again, but I will put a link to those videos in the description below. Finally, we sort the eigenvectors in order of decreasing eigenvalue, so the eigenvector with the largest corresponding eigenvalue is first, followed by the second largest eigenvalue, and so on. And that's actually all that we need to do. We can then just return the resulting eigenvectors, as they are actually the principal components. Okay, so I just wanted to give a quick example of an application of PCA for dimensionality reduction. And this can be essential for data analysis in situations where we have data with very high numbers of dimensions or variables. And PCA can help us in this situation by allowing us to choose only as many principal components as dimensions that we want. And actually we saw this really in the video that we were looking at just now. So we know that the first component is going to contain most of the information from the data, or is going to describe most of the variance of the data. And the second component will describe the second largest amount of variance, and so on. So we know that if we include the first two principal components, then we're going to include a significant portion of the variance of the data, or indeed the information contained within that data, and we can disregard the rest. And that's the basic principle really of dimensionality reduction. We reduce the number of dimensions or degrees of freedom or variables, whatever you want to call it, of our data, but we do it in such a way that we try to preserve as much of the information as possible, and PCA provides a really good way to do that. So, for example, we could reduce the three-dimensional image data that we were just looking at into 2 dimensions. This could make it easier to analyze, depending on what we wanted to do with it. To perform dimensionality reduction like this, we need to be able to transform our data using the principal component vectors. If we have the eigenvectors of the covariance matrix, the principal components, expressed as columns of a matrix as shown here, along with the eigenvalues, we can then sort the columns of V in order of decreasing eigenvalue, as we've just said. So we end up with the eigenvector that corresponds to the largest eigenvalue in the first column of V, followed by the eigenvector corresponding to the second largest eigenvalue in the second column, and so on until we build up V. Okay. We then keep only n columns of V, where n is less than or equal to p and represents the number of dimensions that we want our result to have. Okay, so p was the original number of variables, n is going to be the number that we want to keep, okay, which it would typically be less than p. And that would give us v hat, which we can then use to transform our original data to give x hat, as shown here. X hat will now have n columns rather than the p columns of the original x. And that's really actually enough of the theory to be able to implement PCA and apply it in a simple way for dimensionality reduction. As you can see, it isn't actually all that complicated. I think if there's any questions that you may have, hopefully more will become clear when we go to look at the C++ code. So I think we should go and do that now. Okay, so actually looking at the code, this perhaps does look quite long, but it really isn't, and there's just a little bit of fiddling around to do to be able to implement things like computing the column-wise means and so on, as we just saw in the pseudo code. So as before, as with all of the functions within the linear algebra library that I'm putting together, I've created this as a header file. I've talked about that before and the reasons for doing that, because we're using templates and you just have to do everything in header files. I just use the .h extension for my header files, but some compilers will require .hpp because they are C++, so that does make sense, but if your compiler is one of those, then you can change accordingly. Otherwise, the code here really follows pretty much the same basic format that we've used for everything else so far as part of this library. We have our include guards and things as normal, and as well as a variety of things from the standard library, we bring in qbmatrix.h, qbvector.h, and qbi.h. qbi, of course, that we worked on in the previous video in this series when we looked at implementing code to compute the eigenvectors and eigenvalues of a given matrix. Okay, so we then define 2 error codes for matrix not square and matrix not symmetric. These, of course, are also present in the eigenvector code, but I wanted specific PCA equivalents of those. And then one thing that I have done differently to other functions is that I have put all of the code here within a namespace called qbpca. Now, the reason I've done that is that we have a number of different functions here in order to make it work, and this isn't a class or anything like that, so these functions are callable from anywhere, and in order to reduce the chance of sort of function name conflicts or whatever occurring later, I thought it made a lot of sense to put this into a namespace. Now I do intend ultimately to go on to put all of the code for this into a QB-linalg namespace and tidy it up accordingly, but it just seemed more important to put the PCA code into a namespace up front. So we've already seen the maths of how we go about using computing the eigenvectors of the covariance matrix in order to get the principal components, and we've seen why, and we need to subtract the column-wise mean. So the first thing that we have here is a function that allows us to do that. So this is, of course, templated to type name t, so the user can use this with any data type that they wish, although in reality, as I've said before, at the moment, actually only floating point data types are supported. Anyway, so we are going to return a standard vector of type t containing the column means. Our function is called compute column means, and we accept as input a const reference to our input data of type QB matrix 2. We simply determine the size of the data from num rows and num cols, as you can see there, and we create a vector for the output, also of type t, and then we're simply going to loop through and compute the mean of every column. So we loop j from 0 through to the number of columns, we initialize a cumulative sum variable to 0 of type t, and then we simply loop through all of the rows, I from 0 to num rows, and cumulative sum plus equals input data get element ij. That's pretty obvious. And then we push back into the output the cumulative sum divided by the number of rows, which will of course be the mean, okay? And then we simply loop through and we do that for every column and return the output. So the output of that function is simply going to be a standard vector containing the column means for each of the columns, so one element for each column containing the relevant mean, okay? The next function that we have is one to actually perform the subtraction, to subtract the column means from the given data. So this is simply void, it doesn't return anything, subtract column means, accepts as input a reference to the input data. Notice this is not const because we're going to modify it, and it accepts also a reference to the column means, an std vector type object containing the column means. As before, we determine the size of the data. And then very simply we loop through j through the number of columns, I through the number of rows, and then we just need input data.set element ij, comma input data.get element ij minus column means at j. Okay, so really quite straightforward. Okay. And then we come to the function to compute the covariance matrix. Now this is pretty straightforward. We're just using the x transpose times x methodology that we saw before, and I've written in the comments here, note that we're using x transpose x rather than xx transpose, as is the way it is usually written, and that is because of the way that I've assumed for my application the data is going to be arranged with one row for every observation and one column for every variable. Okay, so be aware of that. Depending on how your data is formatted, that might be something you need to change. We then simply get the number of rows, and we define a new QB matrix 2 object, which we're calling covx for covariance of x, obviously. And then we simply have 1 over the number of rows minus 1 multiplied by x dot transpose times x. So here we're really benefiting from all of the work we've done up to now building this linear algebra library, because that's all we need. And then we return the covariance covx variable as required. Okay, and then lastly we have a function that actually computes the eigenvectors of the covariance matrix. This returns an integer for the return status. So this is a function where interesting things could go wrong, and you want to be able to return a meaningful error code rather than simply like, ooh, no, it didn't work. I like to try and return something that indicates why it didn't work, so it might be more useful to the user. So we accept as input a const reference to our covariance matrix, of course, of type QB matrix 2, and also a reference to a matrix into which we're going to put the eigenvectors. Okay, because we're using our output variable for our return status, then we have to return the eigenvectors into a variable defined here. So pass by reference makes that really very simple. So the first thing we do, as I've talked about before, at the moment we copy the covariance matrix into X. Now the reason we do that is because I haven't quite tidied up all of the consts within the QB matrix 2 class. It's something I do mean to do in terms of refactoring, and something that I should go and do. But for the moment, because we declare it as const here, which means we can't change it, some of the functionality from the QB matrix 2 class doesn't work. So what we do is simply copy it into a new variable called X, and we work with that instead. Now that would be hugely inefficient if we were dealing with very large volumes of data. I'm well aware of that. And like I say, I do intend to go through and refactor everything to take care of that kind of thing, to make it a little bit better. Anyway, the covariance matrix must necessarily be square and symmetric, otherwise it's not a valid covariance matrix. So it makes sense in this function, I think, to test that. So we simply test if x is not if not x is square, then we return QBPCA underscore matrix not square, and similarly if it's not symmetric, we return QBPCA underscore matrix not symmetric. That's pretty straightforward. We then compute the eigenvalues, very easy to do using the functionality that we developed in the previous video. So we simply create an std vector object of type t called eigenvalues, into which we're going to store our eigenvalues, and then we just simply use the qbeiqr function that we developed in the previous video on x, and returning the eigenvalues into the eigenvalues vector. So that will calculate the eigenvalues of x and store them into eigenvalues. Now we need to sort the eigenvalues. Now we talked about that in the slides just now. We need to sort them into order of decreasing eigenvalue. So we simply do std : sort. We're using the sort function there from the standard library, from eigenvalues.begin to eigenvalues.end, and that will put them into increasing order. So we'll get the smallest eigenvalue first, which is of course the opposite of what we want. So then we use the reverse function again from the standard library, and again over eigenvalues.begin all the way through to eigenvalues.end, and that will give us the sorted eigenvalues in order of decreasing value. Now, one thing that's nice about the code that we wrote in the previous video to calculate the eigenvalues and the eigenvectors is that we calculate the eigenvalues separately to the eigenvectors. And then for each eigenvalue, we go through and we estimate or approximate the eigenvector corresponding to that using the inverse power iteration method. See the previous video for more details. There will be a link in the description below. What's really convenient about that is it means that we only need to worry about sorting the eigenvalues. We don't need to worry about doing any corresponding sort of the eigenvectors, because once we've got the eigenvalues in the correct order, we simply loop through them and calculate the eigenvector corresponding to each eigenvalue, which means that naturally they will be in the proper order. So we set up a vector, a QB vector object called EV, which is going to store the eigenvalue, which has obviously x.numcols elements. We're then going to set up a QB matrix 2 object called EVM for EV matrix, which has x.getNumRows and x.numcols size, so it's the same size as x. But of course, in the context of this function, x is the covariance matrix, so that's important. And what that's going to do is simply we're going to calculate each eigenvector, and then we're going to store it into that matrix so that we can output them all together. We could have outputted them as an std vector of QB vector objects, but I didn't like that. I wanted them to be a matrix because we can then go on to use it for other things, transforming data or whatever, very conveniently. So I think it makes sense to output everything as a QB matrix 2 object. So that's what we're going to do. We then loop j from 0 up to eigenvalues.size plus j, so we're going to use that simply to loop through every eigenvalue. We extract the individual eigenvalue of type t, so ti equals eigenvalues.addj. Okay, so each eigenvalue, now I'm aware you can loop through an std vector object using iterators, but see, it does, as far as I understand it, it does get quite complicated if you want the iterator variable and also an index, and in this case I really wanted the index, so I went with it kind of using the conventional, you could say old-fashioned approach, but yeah, I think it's good enough. I'm quite pleased with this code. It's more human readable. I think sometimes when you try and do things in the really sort of optimized way using iterators and whatever, you actually lose a lot of human readability. And I'm pretty sure the compiler is good enough to recognize what's going on and make pretty much the same result in the end anyway. So I think it makes sense to write the code in such a way as to be more human readable in this context. Anyway, that's what we've done. So we extract each eigenvalue into the variable called eig, and then we use the qbinv_pit function for inverse power iteration of type t on x and returning we are going to calculate the eigenvectors of the matrix X, the individual eigenvector, of the matrix X, corresponding to the eigenvalue in I, and we're going to return the result into EV, okay? And then we simply loop through all of the elements of EV, and we set the relevant element of the matrix EVM, accordingly using evm.setElement I, j, ev.getElement I. Okay, so that will set every row. Now, this is a little bit messy, and it's because when I created the vector and matrix classes, I haven't really bothered to put in any code to support slicing. And so you can't just like add a column vector directly to a matrix to create a matrix with one extra column. That sort of functionality I suppose would be really quite convenient, but up until now I haven't had any real application for that, so it's not really something I've bothered to do. If it seems like it's going to be something I want to do more and more, then I will go back to QB matrix and QB vector and we can have a look at that, but for now I think it's fine really just to do it this way. We then return the eigenvectors, which is the EVM, so eigenvectors equals EVM, and return the final status, return status. At the moment, actually, we are capturing return status 2 from qbinv_pit. The reason being that we can then capture the return status if it returns maximum number of iterations exceeded, which can be useful information, that we'd know whether it terminated the iterative process because it reached the maximum or whether it terminated because it converged. At the moment, I'm not actually doing anything with return status 2, so that's something to do in the future. Okay, and then we have our final function here. This is the one that actually brings all of that together to calculate the principal components. It's called qbpca. It returns an int for the return status, accepts as input a const reference to the input data, and it puts the output into a QB matrix 2 object called output components. As before, the first thing it does is make a copy of the input data into X. We just talked about that, so don't need to mention it again. We can then compute the mean of each column of X here, which we store into an std vector object called column means, using the compute column means function, passing X as input, and we subtract the means from the data, subtract column means t x column means. We've just talked about those. Compute the covariance matrix there, gives us a QB matrix 2 object called covx, simply from compute covariance, and then simply compute the eigenvectors. We set up a matrix called eigenvectors, and we use the compute eigenvectors function that we looked at literally just now, and we pass as input the covx, the covariance matrix, and the eigenvectors object, and that will give us the output components there in the eigenvectors variable. So we return the output as simply output components equals eigenvectors, and that's it. It's actually really quite simple to implement, largely because of all the groundwork we've done putting together this library so far. But there we are. So I think the next thing that makes sense to do, let's have a look at the test code that we can use this. And as before, all of this code will be available on the GitHub repository, linked to that in the description below, sometime soon after the video goes live, not necessarily immediately, but as soon as possible. Okay. So this is the test code that I've put together to test the functionality here. Now, do bear in mind, as I always say, if you're going to use this code for anything yourself, do test it thoroughly with your own data. Don't just rely on that I say that it works. I obviously do make the best effort that I can to make my code correct and free of bugs and errors, but I cannot obviously offer any guarantees. So you are strongly encouraged to do your own testing. Okay, so this follows the format I've used for all of the test code so far, nothing really new there. For my test code, I do using namespace std. This is not generally good practice, I know that, but for my test code I do a lot of couts and things, using a lot of things from the standard library, so I think in this context it's really okay to do that. So we bring in QB matrix, QB vector and QB PCA, of course, and within int main, obviously our entry point, we tell the user what we're doing, and we're going to test using 100 observations of 3 variables, which we're getting from a .csv file that I have created and will be included in the GitHub repository. Okay, so the file is called qbpca_testdata.csv, and we're going to read that in. In order to achieve that, it's annoyingly difficult actually to read a CSV file into C++. Well, not difficult, but a bit fiddly. So we create a number of strings, one called row data and one called number. We need a string stream object called row data stream, and we need an std vector type double test data into which we're actually going to put the data that we read, and we need 2 integer variables to store the number of rows and the number of columns. Now I've written this to be as flexible as possible, so it should work with any number of rows and columns in the CSV file that you wish to use, but we have 100 observations or 100 rows of 3 columns in this example. We then open the file, so we create an ifstream object called input file, and then if that's open, we display a message to say we've opened it, and then we loop until we reach the end of the file. Within that loop, we get the next line of the file using getLine, input file into row data, so row data is a string, okay, you can see that there. We're then going to loop through and extract the individual numbers from that. So we set row data stream.clear to make sure we clear everything from the stream, and then we set the string input to the row data stream to be row data. So we read the line into the string row data, and then we pass the string row data into the row data stream object. Okay. So if the number of rows is less than 1, then we set numCols to 0. This is a slightly, I'm not too pleased with this way that I've done it, but it does work, and this is only my code really to test PCA, so I wasn't too worried about it, because we only want to count the number of row columns when we're dealing with the first row. So if numRows is less than 1, we reset set numCols to 0. Okay. We then loop while row data stream is good, while row data stream.good. So what that means is that we'll loop through the characters from all through the string stream object that we've created called row data stream, and we can look at each one accordingly. So we use getLine, row data stream into the string called number separated by comma. Okay, now we can use this delimiter here with getLine in this context because we're using this on a string stream object, okay, and not on the file. We can't do that directly as we read data in from the file, as I understand it. This functionality is specific to the overloaded version of getLine for dealing with string streams, as I understand. If you know different, do please let me know in the comments. I would love to know if there's a better way of doing this. And then we simply do testdata.pushback, and then a to f at number.cstring simply converts our number to a floating point from a string to a floating point number, which we push into testdata. And there we go. And then if numRows is less than 1, we increment the number of columns. So number of columns will ramp up until we're no longer looking at the 0th row. Once we're beyond the 0th row, numCols is fixed. And then we simply increment numRows, and we go back up to here, and we continue with that until we reach the end of the file. So a slightly messy way of doing things, but it does work. That will read in a CSV file, giving us all our data arranged into test data, and with numCols and numRows populated accordingly. We then close the file, and the one thing to note is the above code does read 1 line too many. I'm not sure exactly why. Again, if you know why, please let me know in the comments below. I would love to know as well. So simply to take care of that, we decrement numRows by 1, and we do testdata.popback, which removes the last element from the test data vector. Okay. And we then display that we've completed reading the file. We say how we've read how many rows, consisting of the number of rows of observations, a number of columns variables, constituting the total number of elements, so we can verify that we've read everything correctly. We form that into a matrix. We simply create a new QB matrix 2 objects of type double called X, consisting of num-rows, num-cols, and test data. So that will create the matrix object with the data that we've just read. And then we're going to look at using these functions separately so that we can test that they work, and then we'll look at testing everything all wrapped up together. So first off, we compute the covariance matrix. We create a vector of type double, column means, which we then call QBPCA colon compute column means, and we copy X into X2, and then we use the QBPCA colon subtract column means function to subtract the column means from X2. Okay? And then we use the compute variance function from our QBPCA namespace on X2 to calculate covx, which should then contain the covariance matrix, which we then display. And we can calculate the covariance matrix for the same data using other software, and we can verify that they do indeed match, and that is what I've done. We then can calculate the eigenvectors using QBPCA compute eigenvectors of the covariance matrix and store the result into the QB matrix 2 object here called eigenvectors. And we print them out using eigenvectors.print matrix. Okay, pretty straightforward. And then finally we test the overall function to see that we do indeed get the right result. So create a new QB matrix 2 object here called eigenvectors 2, and then we use QBPCA QBPCA x and eigenvectors 2. So that will perform the whole operation on the original data and put the result into eigenvectors 2. Okay, and we print that out and display what the final test result 2 is. That the output condition of QBPCA, and then we simply print out the final eigenvectors, and the eigenvectors 2 and eigenvectors there should be identical. And then I've gone on to actually test dimensionality reduction. Now, actually, before we talk about that, if you were to plot this data originally, you get a plot that looks like this. So this shows that we have it's three-dimensional, obviously, because we have 3 columns and 100 rows. So here we get 100 points, which are scattered about the line z equals x plus y, around the plane, sorry, z equals x plus y, as you can see on the plot here. And the eigenvectors, our final result here, the eigenvectors that we get in eigenvectors 2 here, these are, of course, the principal components. So if we plot onto this the first 2 principal components, like you can see here, you can see that those do indeed correspond to the axes of greatest variance for the data, which is, of course, exactly what the principal components are supposed to be. Now, I haven't plotted the third principal component here because it would be orthogonal to these 2, and it's the amount of variance that it contributes to the data is tiny, so I just left it off. So we've only looked at the first 2. And what we're going to do actually is go on to look at, as an example of dimensionality reduction. So we're going to use this data, we're going to reduce it from 3 columns to 2, and we're going to have a look at what that looks like. So here we simply tell the user what we're doing, testing dimensionality reduction, start with x, which has num rows, num cols, and I'm going to use only the first 2 principal components. Now, to achieve that with my code is quite easy. We create 2 new QB matrix 2 objects, both of type double, called V and part 2. So V is going to contain the principal components that we're interested in, and part 2 we don't really need to worry about, it contains the other part. And we use the separate function that we created as part of the QB matrix 2 class when we were looking at Gauss-Jordan elimination many episodes ago now. So we simply do eigenvectors.separate V. What it will do is separate the eigenvectors matrix into 2 matrices, one called V and one called part 2, around or just before column 2. So that will put the 0th and 1st, or 0th and 1th, if you like, columns into V, and the 2nd column into part 2. And then we're only interested in V, so you do v.print matrix. And note I've created an overload version of print matrix in the QB matrix 2 class. It doesn't really need any explanation. It's in the GitHub repository, so you can go and have a look at that if you want. But it simply allows you to specify the precision to which you wish to display the floating point numbers. So we do that to 8 decimal places. Okay. So we then calculate our new x, which is our new data. So we set up QB matrix 2 of type double for new x, that's this one. And we now are going to transform the data using the equation that we saw in the slides just now. So we have v.transpose times x.transpose, which is all of that, dot transpose, so transpose the whole thing, and that will apply the first two eigenvectors that we've put into V as a linear transform to the data in X, and it gives us the new result called new X, okay, which will now have only 2 columns but still 100 rows, and we display new X dot get num rows and new X dot get num cols to verify that. And then it's so much simpler to write a CSV file. We write that out as a CSV so that we can check it or plot it or do whatever we want with it. Really the same scheme. We do OF stream, output file name there, QBPCA test data underscore reduce.csv. If the file is open, we simply loop through every row of new X and do output file, put into that new X dot get element I, 0, comma, new X dot get element I, 1. Okay, and that's that. And for tidiness, I do prefer to put a space in there like so. Okay, and then output file dot close, and that's it. Okay, so just to prove that that works, if we go to the terminal, and if you clone this from the Git repository or download it from the GitHub repository, then this is what you're going to see. And inside test code, the test code directory or folder, there we have QBPC test code underscore QBPCA, and we can compile that simply with G++ -o test code underscore QBPCA. And the file we want to compile is test code underscore QB pca.cpp -std C++17, and we just let that compile like so. And let's just clear the screen at /test code underscore QB PCA. If we run that code, then we see all of the results. So we first test with 100 observations of 3 variables. We've opened the file successfully. We completed reading the file. We read 100 observations of 3 variables, so that's good, constituting 300 elements in total. So we know that we successfully read the file. It gives a covariance matrix, as you can see here. Again, this data will be available in the GitHub repository, so feel free to go and check in any other software you wish, and I have tried that and I get the same results. So as far as I'm aware, it does seem like everything works correctly. We get the following eigenvectors of the covariance matrix. Now, one thing to note of those, as I said in the previous video, the signs of the eigenvectors can change. So for example, the first eigenvector here of 0.331, 0.296, 0.896 is all positive. In some other software, depending on the technique that they've used to get the eigenvectors, those might be all negative. But whether an eigenvector is positive or negative, that's simply a scaling by -1, and the eigenvectors, it doesn't matter if we scale them. So scaling by -1 doesn't really change anything important, so we don't worry about that. So if you check in other software and you find the signs of the opposite, actually a good example is the second one here. The opposite of that would be plus 0.685, minus 0.729, and minus 0.012. That's fine. They are equivalent, so don't need to worry about that. And then we test the overall function, which gives a return status of 0, indicating success, and the final eigenvectors we see are exactly the same as we get there, so that's what we would expect. And testing dimensionality reduction, we started with X with 100 rows and 3 columns. We use only the first 2 principal components that we've displayed here, and the result is 100 rows and 2 columns, which is exactly what we would expect, and gives the resulting 2-dimensional plot that you can see here, where the axes U and V correspond to the 2 principal components that we kept, and you can very clearly see they capture practically all of the variance of the data, which is precisely what we wanted to see. Okay, so there we go. That's really everything that I wanted to talk about in terms of the code. We've looked at the code required to create a simple implementation of principal component analysis, and we've looked at a very simple test case based on a very small data set consisting of 100 rows of 3 columns. As I've always say, if you want to use this code for anything yourself, really do make sure you test it thoroughly first. My code is really intended to be more for educational purposes than anything else. There's usually more optimum ways of doing things than I do them in this code, so just be aware of that. But otherwise, there we go. That is principal component analysis. So there we go, that's really everything that I wanted to talk about today. We've had a look at principal component analysis, or PCA, in terms of looking at some examples of things we can do with PCA. We've then looked at some of the maths behind principal component analysis and how it works, and also how we can actually implement it. And then we've gone on to look at how we can implement it in C++ using the linear algebra library that we've been putting together over the last 14 episodes of this series. Anyway, so I really hope that's been of interest. There are obviously many more possible applications of principal component analysis than I could realistically talk about in this video, so plenty that you could go on to do with it, but I think, as I say, this video is kind of long enough already, so I think we're going to leave it there for now. Okay, anyway, I really hope you've enjoyed it. It's been a great deal of pleasure making it. I hope it's useful and inspiring to at least some of you out there. If you have enjoyed this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so you don't have to miss any future videos. Thank you very much. Anyway, as I say, it's been a pleasure. I hope you've enjoyed it, and I really look forward to seeing you in the next video. Thank you very much for watching. Bye.